right, we're back for 3.3, which is increasing and decreasing functions and the first derivative test. Let's get some definitions down first for increasing and decreasing, and then we will learn all about the first derivative test. We have to be very careful with our wording. We have to articulate our words very carefully, and it's very easy to say the wrong thing. So I'm going to do the best that I can. Hope I don't mess up as well. All right, let's start this out. Definition. A function f is increasing on an interval if for any two values, x1 and x2, in that interval, x1 less than x2 implies or means that f of x1 also has to be less than f of x2. Now, obviously these are x values, and f of x1 and f of x2 represent y values. So if x1 is smaller than x2, then pretty much y1 has to be smaller than y2. Let's take a peek at these pictures that I obviously drew some increasing functions. It doesn't take too much to realize what increasing means, pretty much going up. But mathematically it has a little bit more of a technical meaning to it. As you scan your picture from left to right, x1 is less than x2. That satisfies the given over here, or the hypothesis, so to speak. x1 is less than x2. x1 is less than x2. x1 is less than x2. And now, what does f of x1 have to be? It has to be less than f of x2. And since these are y values, it means that the y value at x sub 1 has got to be lower than the y value at x sub 2. So as I go from left to right, x sub 1, x sub 2, f of x sub 1, f of x sub 2. You can see your y values are getting bigger. So if the first x value is less than the second x value, then the first y value is also less than the second y value. That is the mathematical definition of an increasing function. Now I drew you a nice linear function here. This function is definitely increasing. Okay. Let's just call it f. F is increasing. F prime is what? What is the slope of all my tangent lines along this function? F prime is positive, is the word I'm looking for. And you might have been thinking constant, and it is constant as well. But that's only because f in this case is linear. If I move to a different example that's not a nice straight line, I won't be able to say constant, but I will still be able to say positive. So let's move along to this one. X sub 1 is less than x sub 2. F of x sub 1 is less than f of x sub 2. Okay? So I still have the fact that this function f here is increasing. Alright? I still have the fact that f prime is, and now we take our handy dandy tangent line and we take a peek at each of these tangent lines as you follow along the curve. Positive slope, positive slope, positive slope, positive slope, positive slope, positive slope. Every single tangent line as I follow along this curve is going to have a positive slope. So I say f prime is positive. And it just so happens for this particular example that f prime is not constant, but what other word could we give it? We have a slope about like this. It's positive, but not very steep. We have a slope here. It looks like it's about a positive 1. We have a slope here. It looks like it's maybe positive 2 or 3. We get the slope is getting steeper and steeper and steeper. The slope is getting higher and higher and higher. So the slope itself is increasing. All right? This is because f prime right now happens to be concave up. Let's take a peek. And you know what? I think I'll move this over just a little bit so we don't get confused on which example we're looking at. Let's go ahead and deal with an increasing function like that. And I'll go ahead and mark my x sub 1, comma, f of x sub 1. And up here I'll put x sub 2, comma, f of x sub 2. So notice, from left to right, my x sub 1 is less than my x sub 2. but my f of x sub 1, I shouldn't say but, I should say and, my f of x sub 1 is also less than f of x sub 2. So f is increasing. F prime is, now let's take a look at the slope of the tangent lines. Positive slope, positive slope, positive slope, positive slope, positive slope, positive slope. We're thinking maybe it might zero out, but right here it hasn't anyway, right? The slopes of all these tangent lines are positive. Okay? And I might want to talk about the slope here a little bit. What are the slopes doing? I start out pretty steep. Not so steep, not so steep, not so steep. And we actually said we thought it might be actually leveling off, going towards a slope of 0. So I'm going from a pretty good steep slope towards something that's a lot smaller. So my slopes indeed are decreasing in this example. Okay, f prime itself is decreasing. And I'm going to tell you here that that's because f prime is, take a guess, concave down. This is concave down, concave up, and there's no concavity here whatsoever because we're neither concave up nor down. All right, just to get an idea what f is doing when you're increasing. I could be increasing just consistently like a straight line. I could be increasing more and more and more and more and more every time I turn my tangent line, or I could be increasing a little bit less, a little bit less, a little bit less every single time. Okay, there's my definition of increasing. I'm going to put my own little terms over here, and I'm going to say this basically means that as x gets bigger, these are my y's, y gets bigger. That's what I think. I'm also going to say, as you follow the curve from left to right, or the graph of the curve, from left to right. We always read our graphs from left to right. As you follow the graph from left to right, the graph goes what? Up. The graph goes up. The graph definitely increases. Okay, that's our definition of increasing. We're going to go ahead and give us our mathematical definition of decreasing, and I think I can pretty much do that by erasing a few words and swapping them out. So we're going to start with our definition. We're going to say a function f is, instead of increasing, we now switch to decreasing. On an interval, if for any two values, x1 and x2 in the interval, x1 less than x2 is going to imply that f of x1 is, and this is going to say greater than f of x2. Now, I'm going to erase these examples. I don't want you to get these increasing functions confused with what we were talking about with decreasing. And I'm going to erase these words, although I could have left all that X stuff over there because that's still the hypothesis. And now, let's just take a nice linear function and talk about x1, f of x1, compared to x2. And why am I drawing another increasing function? I couldn't tell you. I would like to draw one that is decreasing. Thank you. So this is x1, f of x1. And then this one over here we'll call x2, f of x2. Okay, so as we move from left to right, let's read this. x1 is less than x2. Look at it. x1 is less than x2, which means it's to its left. x1 is less than x2. And look at f of x1. f of x1 is the y value up here. And how does it compare to f of x2? It's higher, isn't it? So therefore it's greater than f of x2. So you get the reverse relationship going on as we did for increasing, which I'm sure you already knew. That is a lot of common sense here. It's just this meticulous terminology we've got to get through. Okay, so I would like a decreasing function, something like this now. So I want to talk about this point, x1, f of x1, and this point, x2, comma, f of x2. Okay, still satisfies the same conditions. My x1 is less than my x2 because x1 is to the left of x2. And my f of x1 is definitely greater than my f of x2 because my y value up here is higher than my y value there. So f of x1 is greater than f of x2. And you can tell it's a decreasing function because you know decreasing means to go down. And the other decreasing example I would like to give you would be something that does something like this. We're decreasing like this. This is x1, f of x1. And down here we'll have x sub 2 and f of x sub 2. Again, x1 is less than x2, f of x1 is greater than f of x2. X's are getting bigger, y's are getting smaller. Let's write that over here. X's are getting bigger, y's are getting smaller, or y is getting smaller. Okay, as you move from left to right on the graph, you go where? And the answer would be down. You go down. All right, let's come over here and talk about this for a quick moment as well. We have the slope of this line right here. We call this function f. F is decreasing. I don't like that. So what is f prime, which represents the slope of all of these tangent lines everywhere along the function? The slopes are all negative. And I know you might say the word constant again. The slopes were constant, right? They weren't changing at all. But the only reason the slopes were constant was because the function f is linear. If you have a linear function, the slope is always constant. Okay, over here, I still have a function, let's call this f again, we'll call that f again. I still have a function f, and it is decreasing. What about f prime everywhere here? F prime represents the slope of each tangent line as you move along the curve. What's the slope doing as you move along the curve? Let's talk about this kind of a slope. This is a negative slope, but it's not too steep at all. This is still negative, but it's getting a little more and more steep, isn't it? Still negative, more steep, still negative, more steep, still negative, more steep, and so on and so on. When negative numbers get steeper and steeper and steeper, or get bigger, like -2, -3, -4, -5, what's the value actually doing? And it should say that f prime is decreasing as well. The slopes are actually decreasing. Think of up here, maybe the slope might be a 0, but it's not quite a 0. We're going to leave it so that we don't see that relative max right there. We're just barely off the 0 part, and we're getting smaller and smaller and smaller and smaller and smaller. So the slopes are definitely decreasing. Well, this is because, let me see here. The function is decreasing, f prime is decreasing, and this is because f itself is concave down. Okay, this is concave down. And you can see this one over here before we even start is concave up. All right, the function itself is going down, so f is decreasing once again. Let's talk about f prime. Anytime we're talking about f prime, we're talking about the slope of tangent line, anywhere you come around here. This is a pretty steep negative slope. And then not so steep and not so steep, and we're actually approaching what? We're not hitting it, but we're approaching a flat point, aren't we? So you're going from something that's pretty steep